Hi everyone, welcome back to our channel. Today we are reviewing the paper Octo, an Open-Source Generalist Robot Policy, authored by researchers from UC Berkeley, Stanford, Carnegie Mellon, and Google DeepMind. This paper introduces Octo, a groundbreaking approach that aims to revolutionize how we train robots to perform a wide range of tasks. Traditionally, robots have been trained individually for specific tasks, which often requires substantial amounts of data and time. But with Octo, the focus shifts towards creating a generalist robot policy that can seamlessly handle multiple robots, tasks, and environments. Let's explore how this works and why is it a significant leap forward in robotics. One of the most significant challenges in robotics is developing policies that are flexible enough to adapt across various tasks and robots. Traditionally, policies have been trained using large datasets of trajectories collected from a single robot. Earlier efforts in autonomous data collection laid the groundwork for scaling policy training, and more recent advancements have combined modern transformer-based policies with large demonstration datasets. However, these approaches often focus on single robot embodiments, which limits the generalization capabilities of the policies. Octo revolutionizes this by expanding the scope of training to include datasets from multiple robot embodiments. Specifically, Octo is trained on Open X-Embodiment dataset, a diverse and expansive dataset that includes 800,000 robot trajectories collected across various robotic platforms. This dataset covers a wide range of tasks and setup, providing a robust training base that allows Octo to generalize better across different robots and environments. This approach contrasts with the previous models like GNM, RoboCat, and RTX, which, while impressive, often require a user to stick to predefined sensory inputs and action spaces used during pre-training. Furthermore, Octo is fully open source and reproducible, setting it apart from many large language models that are not publicly accessible. This makes Octo a powerful tool not just for researchers, but also for developers looking to apply advanced robotic policies across different robots and tasks with minimal fine-tuning. Now let's understand the network architecture that powers Octo. At its core, Octo is a transformer model specifically designed for handling the complexities of robot control. The architecture is inspired by recent developments like the use of denoising diffusion objectives for action decoding, as seen in works by Jonathan Ho. By employing denoising diffusion approach, Octo predicts more stable and reliable action sequences by iteratively refining noisy predictions, leading to smoother robot operations. Another key aspect of Octo's design is the prediction of action chunks or sequences of future action, inspired by action chunking transformer. This allows Octo to plan and execute complex tasks by considering a series of actions in advance, ensuring that each action aligns with the overall goal. Octo's architecture is centered around three main components: input tokenizers, a transformer backbone, and readout heads. The input tokenizers are responsible for converting various types of input data such as language instructions, goal images, and sensor observations into tokens that the transformer can process. For instance, language instructions are tokenized using pre-trained transformer model called T5, which converts the language input into sequences of embedding tokens. These embeddings are compact numerical representation that capture the essence of the language input. For visual data, like images, Octo uses a shallow convolution neural network to break down the images into smaller, flattened patches, which are then tokenized from the transformer to handle. Once tokenized, this input data is fed into the transformer backbone. The backbone processes these tokens, generating embeddings that represent the input data. The attention mechanism within the transformer is particularly powerful here, as it allows Octo to focus on the most relevant parts of the input while considering the sequence of observations and tasks. Octo's transformer backbone uses a blockwise masked attention pattern, meaning that each observation token can only attend to tokens from the same or earlier time steps. This setup ensures that the information flows in a casual, consistent manner, which is crucial for maintaining the sequences of events in robotics. One of the key innovations in Octo's architecture is the use of readout tokens. These special tokens are added to the sequence of the inputs and are designed to summarize the information from the entire sequence up to that point. They function similarly to the classification token in models like BERT, gathering and summarizing all relevant information from the observation sequence. The action head in Octo then uses these embeddings generated by the readout tokens to predict a chunk of future actions, allowing the robot to execute complex tasks smoothly. What really sets Octo apart is its flexibility during fine-tuning. When adapting Octo to a new robot or task, the model allows for addition of new inputs or outputs without needing to retrain large portions of the network. For example, if you need a new camera or sensor input, you can simply add a new tokenizer and positional embeddings while keeping the rest of the model intact. This is a significant advantage over the previous models, where changing the input configurations often required reinitializing and retraining large parts of the model. Octo's modular design makes it a versatile tool capable of handling diverse robot sensors and action configurations, making it a valuable asset for the robotics community. Octo was rigorously tested across various robotic platforms to assess its performance as a generalist robot policy. In zero-shot evaluations where the model was applied to new tasks without additional training, Octo demonstrated strong capabilities across different robots, including the Widow X Bridge V2 and UR5 tabletop. It outperformed existing models like RT1X and performed comparably to the larger RT2X model. These tasks involve challenges such as object manipulation, environmental changes, and varying object positions, showcasing Octo's ability to generalize across various novel scenarios. In fine-tuning experiments, Octo efficiently adapted to new tasks and environment with minimal data, often requiring only around 100 target demonstrations. The model excelled in complex tasks, including precise manipulation and bimanual coordination, consistently outperforming models trained from scratch and other state-of-the-art approaches. Ablation studies further highlighted the effectiveness of Octo's design, particularly its transformer-first architecture and conditional diffusion decoding head, which are key to its superior performance across a wide range of robotic tasks. In summary, Octo represents a significant advancement in the field of robotic learning. By providing an open-source generalist robotic policy that can be adapted across multiple robots and tasks, Octo paves its way for a more flexible and capable robotic system. If you are interested in learning more about the innovative approach, I highly recommend checking out the full paper. Thanks for watching, and don't forget to subscribe for more deep dives into cutting-edge robotic research.